Welcome aboard, where aviation concepts become simple. From instruments to aerodynamics, we make exam prep clear and cockpit learning faster. This is StudyKwik Aviation.
Welcome to StudyKwik. In the last lesson, we looked at the two types of basic design of air temperature measurement devices. These were the direct reading type and the remote reading thermometer. Both types are subject to the three errors of all air temperature measurement instruments: instrument error, environmental error, heating error. Heating error is caused by the movement of the aircraft through the air. The air temperature rises in the immediate vicinity of the aircraft as a result of friction, kinetic heating, and air compression, adiabatic heating. Kinetic heating is the main contributor to the temperature rise in the direct reading thermometer. As speed increases, more and more molecules of air per second impact the flat plate at the front of the probe. This friction causes a rise in temperature. Adiabatic heating is the main contributor to the temperature rise in the remote reading total head thermometer. This occurs due to conversion of pressure energy into temperature energy, not by direct application of heat. For example, boiling a kettle equals direct application of heat. Pumping a bicycle pump equals rise in temperature without any added heat, because compressing the air converts energy. Pumping a bicycle pump equals rise in temperature without any added heat, because compressing the air converts energy. In the remote reading temperature probe, outside airflow, which may be several 100 knots, is rapidly brought to rest inside the platinum measurement chamber. The energy of the moving air is released as a temperature rise. This is adiabatic heating. Now, let's show these combined effects on a graph. Y-axis equals temperature, x-axis equals aircraft speed. The temperature of undisturbed air before the aircraft flies through it is what we want to measure. This is called static air temperature, SAT, often written as TS. But because of heating error, the temperature measured is higher than SAT. If there were no measurement losses, we would measure total air temperature, TAT, written as TT. The difference between SAT and TT is called total ram rise. The laws of thermodynamics tell us kinetic heating plus adiabatic heating equals total ram rise. TAT is defined as the maximum temperature attainable by the air when brought to rest adiabatically. However, real instruments always have inefficiencies. The actual rise measured equals measured ram rise. The actual temperature seen equals ram air temperature, RAT. The ratio of measured ram rise to total ram rise is called the recovery factor, KR. Example: suppose total ram rise is plus 30 degrees Celsius. Due to inefficiencies, measured ram rise equals 90% of 30 equals plus 27 degrees Celsius. Recovery factor is 0.9, 90%. If SAT equals negative 60 degrees Celsius, then TAT, theoretical, equals negative 30 degrees Celsius. RAT, measured, equals negative 33 degrees Celsius. This, negative 33 degrees Celsius, is what you would see on the ram air temperature gauge. Now let's understand the errors in more detail. Instrument error. This is caused by imperfections in the thermometer's design or calibration. For example, small inaccuracies in the bimetallic strip or the platinum resistance element can result in slight differences between the actual air temperature and the displayed reading. Environmental error. This occurs when the temperature probe is influenced by surrounding conditions. For instance, sunlight directly heating the probe, heat radiated from the aircraft skin, or disturbed airflow around the fuselage can cause incorrect readings. Heating error, explained in Part 1, caused by kinetic heating, friction of air molecules hitting the probe, and adiabatic heating, air compression when brought to rest. This makes the measured temperature higher than the true outside air temperature, SAT. To overcome these errors, modern aircraft use total air temperature TAT probes with specific design features. They are carefully positioned outside the aircraft to minimize environmental error. They are streamlined to reduce frictional kinetic heating. They use correction factors to convert the measured RAM air temperature into the true SAT static air temperature. Direct reading thermometer. Example: a bimetallic strip thermometer works on the principle that different metals expand at different rates when heated. Two metals, such as invar, low expansion, and brass, high expansion, are bonded together. When temperature rises, the strip bends because one metal expands more. If the strip is wound into a coil and fixed at one end, any temperature change makes it rotate. This rotation moves a pointer on a dial, giving a direct reading of temperature. Advantage: simple and reliable. Limitation: prone to heating errors, so suitable only for low-speed aircraft. Remote reading thermometer. Example: modern high-speed aircraft use platinum resistance thermometers. Platinum is used because its electrical resistance changes predictably with temperature. The probe contains a platinum wire coil. As temperature changes, resistance changes. This resistance is measured electrically, and the result is displayed on cockpit instruments. Advantage: more accurate and can be corrected for errors. Limitation: still subject to heating errors. Needs correction. Key point recap. SAT stands for True Outside Air Temperature, which is the desired measurement. TAT is the temperature if air is brought to rest adiabatically, theoretical. RAT is what is actually measured, slightly less than TAT. Recovery factor KR corrects RAT to get closer to SAT. Now let's focus on total air temperature TAT probes used on modern high-speed aircraft. A TAT probe is placed in the free airstream, usually on the nose or fuselage, where airflow is least disturbed. The probe measures RAM air temperature, RAT, which is then corrected to obtain the static air temperature, SAT. To minimize heating errors, the probe is shaped like a small pitot tube with airflow slots that allow excess heat to dissipate. The correction is based on the formula TAT equals SAT times 1 plus R times gamma minus 1 times m squared, where R equals recovery factor between 0.98 1.0 for modern probes. Gamma equals ratio of specific heats, approximately 1.4 for air. M equals Mach number. This correction ensures that the displayed temperature is close to the true outside air temperature, SAT. Even with modern probes, some errors remain. Position error. If the probe is not located in a true free stream position, disturbed airflow can affect accuracy. Time lag error. Sudden temperature changes may take a short time to register. Icing error. In icing conditions, probes may accumulate ice, leading to incorrect readings unless probe heaters are used. To reduce these, probes are electrically heated to prevent ice buildup, aerodynamically designed for smooth airflow, calibrated for accurate recovery factors. Performance calculations. Air density depends on temperature, and density directly affects lift, thrust, and engine efficiency. Altitude indications. Pressure altitude and density altitude are temperature dependent, so OAT corrections are essential for accurate readings. Weather and safety. Icing forecasts and turbulence detection rely on precise OAT data. Fuel efficiency. Modern jet engines optimize fuel flow using corrected SAT readings. Direct reading thermometers are simple but less accurate. Remote reading thermometers are more accurate and used in high-speed aircraft. TAT probes provide corrected readings of SAT, factoring in recovery and Mach number. In short, measuring outside air temperature, OAT, is not as simple as just sticking a thermometer outside an aircraft. It requires corrections and specialized probes to ensure safety, efficiency, and accurate performance calculations. Quick recap: accurate outside air temperature (OAT) measurement is critical for safe operations, performance calculations, and weather awareness. Direct reading thermometers like the bimetallic strip are simple but suited only for low-speed aircraft. Remote reading thermometers, such as platinum-resistant sensors, provide precise measurements for high-speed aircraft. Total air temperature (TAT) probes are widely used on modern jets, correcting for kinetic heating and Mach effects to give reliable static air temperature (SAT). Errors such as position effects, icing, and time lag must always be considered and minimized. Why this matters: flight safety prevents hazards like carburetor icing, turbine flameouts, or inaccurate altitude readings. Performance: accurate temperature ensures correct engine power settings, takeoff calculations, and fuel efficiency. Weather awareness: pilots rely on OAT data for detecting icing conditions and turbulence zones. In summary, air temperature measurement is far more than a thermometer reading. It is a calculated, corrected value that keeps modern aviation safe, efficient, and reliable. Thank you for watching this lesson on air temperature. If you found it helpful, don't forget to like, share, comment, and subscribe to StudyKwik Aviation for more clear and exam-focused aviation concepts. Fly smart, study smart.